locally. So I'm going to record that in case if you need this later or anyone else need this later. So you will get this kind of environment, and this is just Python, but in cells. So there are cells and you can execute code in those cells separately. And it's as simplified as possible, so without any main functions or anything like that. Like this. So it's like IDE and the terminal in the same space. We can do all the regular stuff here. How much are you familiar with Python? So how comfortable would it be for you to start doing computer vision in Python?
I have like last semester I took intro to AI, and I think I used this the notebook, and I've dealt with Python before.
Great, so we can just open it without downloading anything. If you could open it now, it would be awesome.
Yeah, I will try this.
Okay, so I'm going to go through the things that were briefly discussed last time. We have the videos, but it would be, I think it would be nice to have a conversation, I mean, in a format of dialogue about all of those things, because they could be a bit alien. So let's talk about all of that. And the best thing that you can do is to disagree and ask questions, tough questions, especially. They are awesome. So it would be great if we can discuss stuff. And what do you think about the other students joining? Will they be here or not really? Not today.
One student, she told me she will drop out. She will not come anymore. So
one of those.
So we're expecting it. Yeah,
one
new
of three.
ones who came. Yeah, one of those who came last week.
Wow. Sad to hear that.
Yeah.
And so there were three of the students.
I believe so, yes.
And Ahmed. So you don't know if he is going to join. Okay.
Not really, but it does not help that everyone is running with the exams, you know, those days, midterms.
Yeah. That's a tough situation, and Ramadan is beginning soon, so we'll have to.
Yeah, midterms and Ramadan will start. It's really tough.
Yeah,
I
tight
talked
schedule.
with Dr. Hamad. We'll discuss later on WhatsApp. Inshallah.
Yeah. I mean, you'll discuss with him or with me?
And I already I talked with him, but he's not here today. I don't know where is he. He did not respond. He did not come to the meeting. So
okay, got it.
Got it. That, yeah. Yeah, we need to get this information, you know.
Okay. Anyways, we're going to hold this session regardless of the circumstances. So, Abdullah, open your mind. I really promise you that if you do, it would be cool. So let's try doing something with the images. Are you in the comfortable environment? So it is comfortable for you. Everything is fine. You're not in a rush. You're not in the bus. I don't know. So you can focus, right? On this right now. or it's difficult?
I'm actually, it's a little difficult because I'm currently heading home, but I'll be, I can discuss with you like, or like review the previous notes about the OpenCV that we talked like last week. But I'll be arriving in like, I'd say like 20 minutes, I hope.
20 minutes. Okay, so now you can ask anything, and after you will get home and it will be comfortable for you, we can proceed to the coding stuff and all that thing. So if there are any questions that you're comfortable asking right now, you can do that. Otherwise, we can be back in 25 minutes or something. So it's up to you because you're the only newcoming student
Private session.
today. So I'm fine with both ways, really. I'm here anyway.
Yeah, I want to ask, like, we will only be programming only, like we will not be doing any embedded systems or like with the robot, right?
Let me show you. So I am the computer vision guy. I'm doing computer vision. I'm teaching computer vision. And we will be dealing with code and cameras and data from the real world regarding the computer vision. It all starts with the signals that are coming from the world to these cameras. And the answer is yes, we're going to do that during this course. However, there is a PhD student from our team, Fedor, and he is in Khalifa in person in order to work with this hardware. I mean, not exactly this robot, but the others that are at KU at the moment. So with him, you're going to do it's not embedded like Internet of Things, but it's an autonomous robot, really. It's a computer that is capable of walking. Hi, Nasiba. So there will be two directions. The first is computer vision, and the second is the mechanics, materials, 3D printing, working with servo motors, all that thing, and also the hands-on experience in order to compete in May, in June, and further.
I see. I have another question. Like, I believe last time you explained the schedule. Like, what we learned like about PIDs and how to program them and this.
The course in computer vision doesn't really have anything about control and PIDs as well, so we don't talk about that. We have talked about PID control during the summer internship that was held in summer last year. And we actually have a course on control. We are delivering it for our own master's program. But for now, this course is not added into the Khalifa curriculum. So if it will be fine with the requirements and with the plan, we can talk about stuff. There's no problem. There is material and we can do that. But as far as I get it, the plan that was discussed with the management and with the heads of everything in the university, the plan was to do a course in computer vision. And the thing that Fedor will be doing is the hands-on practice. So we're not going to talk about control specifically. However, of course, PID control and other types of control are widely used in these robots. And yeah, they are for sure needed. You're into control already, so you already know about PID, or you know and you want to learn some other things.
I have basic knowledge about PID tuning, but it's very fundamental. I'm not a very I want to be an expert in the control field.
Mm. Okay, got it. So if everything goes well, we're going to have a separate course on control, approximately master level, but I mean, a course for you, but it will be the same material basically that we are delivering here for master students. So it's purely about control. We are starting with describing dynamical systems. We're trying to find the proper approximations, discretization, linearization of the systems, and then we are trying to drive them to the desired state, given the control that we have. So yeah, we can do that, but not during this course, I think. And was there a question about the timings or not? I mean the schedule. Yeah, about the schedule. So the schedule is the following. We're starting with the first practical thing today. You will have a week to check the lectures, and next Wednesday, the same time, or maybe at 20. I mean at 8 p.m.
Yeah.
UAE
Yeah, we'll
time.
check it because I checked again and it seems like 9, not 8 is better.
9
9,
9 UAE time.
UAE time, yes.
Okay, so at this time, we're going to have our sessions during the Ramadan, and after that, our sessions will be 6:30 again, UAE time. So our sessions are up to 3 hours, as long as there are any questions. But I firmly believe that if we're going to start at 9, we'll be not
1
here.
hour, I think.
Maybe, maybe.
Something like this. I think 3 hours a lot if we start.
Yeah, sure. Yes, yes. So finishing the studies at midnight, it's not cool.
Yes.
But it's for math. After that, we are going to start at this time. So the general idea is the following. We check up on some topic, then you watch the lectures. On the next one, you watch the seminars, you perform some activities with the seminar code and with home assignments, and then we basically do it again. That's the format we were working with last semester. There are actually 2 students. We have 2 students joined who were attending in the last semester. So you can ask them, I mean, from their perspective, or you can write them, I guess, or meet. So I can tell about this course only from my perspective, clearly. So we can check for private feedback. That makes sense to understand if that's your cup of tea or not. But if you want to learn about control, I think it's your. Anyways, computer vision is a part of control. It's a part of state estimation.
I just have a comment. I believe like last year, I worked on a robot project, and it had a Raspberry Pi camera. It was pre-programmed, like I bought the robot with my team, so that the camera was programmed to, when you place a specific object with a specific color, the camera, it has a motor, and this motor, it will follow this object wherever you move it. So we will be doing the same thing like this?
Yes, we'll be doing this and other stuff in the field of classical vision. So we're going to detect objects by color. We're going to work with shapes, contours, background subtraction, various types of classical processing. It's basically digital signal processing for high dimensional signals. That's what we're going to work with. So yes.
Also, one last thing, are we going to receive official certificate after we complete the course, inshallah?
Bushra, could you enlighten us on that?
From our side, I do not believe so, honestly. We are working on getting some volunteer hour, but no promises yet. We're still trying to get that, but uh, I don't think so, no.
There are a lot of students that were attending last semester. So how are you doing? Are there any questions? Maybe about robotics in general? We're waiting for the beginning of the practical part, so we can discuss stuff, anything. By the way, if all of us are interested in control right now, we can, well, and if there is only one student that was not listening to these things previously, we can talk about control now and start with vision later. I mean, if it fits everyone, I'm just saying, just proposing. So we can talk about control if that's the topic for you to enjoy.
Yes,
I'm open to that.
Abdullah, what do you think?
I'm okay as long as I learned something new.
Great. So how long will it take for you to get home and get comfortable with the full attention here?
Like around 10 minutes, yes.
Right. Okay. So what I propose to do is I'm going to rearrange stuff, and we'll use this whiteboard. We'll talk about control. Why not? So of course I'm going to place it on the table. I will not holding my laptop like this. But another question is, do you see me mirrored or not?
Yes, mirrored.
Mirrored. Ah, okay. I'm going to mirror the Zoom. There were some settings. All done. I'm going to use this 10 minutes wisely. I'm going to mirror. Where is it? Where is it? Somewhere here, I guess. Yes, here. So now it should be better. You see this, right?
Yes.
Great. Okay, so what I propose to do is I'm going to rearrange things. I'm going to place a chair on a table and place my laptop. And let's talk about control in 15 minutes. Guys and girls who were attending the internship, I think if you have time and if you would like to, I'm going to talk about control, so follow along. You can prepare tough questions about control because right now I feel I can talk about that. I'm into a course in control, so it's it would be fine. It would be fine to talk about that. And what are you doing, by the way? You're about to graduate, right? From the bachelor studies.
Some of us, yes.
Mm-hmm.
Nasib already graduated. I know I will graduate hopefully this semester. Most of the people from last year.
Mm-hmm. Got it. And about the master studies,
I don't think so.
you're planning
Maybe
to
more.
go. You're planning
Like,
to go to the industry.
not necessarily. We have the projects in the university that are very interesting. RoboCup being one of them. A lot of things.
So without master studies.
Because the studies usually they put more pressure on you, and I noticed that you don't really perform well in the projects if you have courses at the same time, and vice versa.
Mm-hmm. Okay, got it. Got it. We can have a separate discussion on that probably at some point. Okay, so let's meet again at 19:15, and we're going to talk about control. So now short break, and then control for as long as you would like to.
All right.
Okay? Yeah. Okay. See you then. I'm going to have a cup of water. I think you can see the writing. So it's 1915. We can start. I would be very glad if you can turn on the cameras if it's comfortable for you. So let's have a more lively discussions as far as we can. Unfortunately, I'm not in person, but anyways, let's try to use the technology to our advantage. And please turn on the microphones to ask if just anything is not clear. That's my fault, and I'm going to work with that. So if something is not clear, that's my fault, and I'm going to accept that. So just pinpoint, and I'll talk about the topic in more detail. Okay. Okay. Great. So everyone is ready.
Yes.
Who else is ready? Okay, but be prepared that I'm going to ask you to ask questions all the time. That's usual thing. So we're going to talk about so-called control. What is that exactly? By control, we mean driving a system that we are controlling to a certain state. It could mean, for example, that we have a humanoid robot. I'm going to approximate this humanoid robot by this thing. And we want this humanoid robot to be at a certain state. It could be a state near a ball, for example. So if we are playing football, the robot is supposed to approach the ball and kick it. What do we need to do that? We, first of all, have to describe the system properly so that we can approach it mathematically, formally. We have to describe it in a vector form. So all of you are familiar with linear algebra, and we're going to talk about those exact vectors. So we're going to try to find the description for the vector for the robot in a vector form. It will be x, and it is going to live in a Euclidean space Rn, where n is the dimensionality of the system. So hold on, let me check. Now that's Zoom trying to, never mind. If we have obtained the state of the system, after that, we have to do some actions that will lead the state of the system to, say, some desired state x hat. That's what we're going to do. So if I'm a robot, I'm here, and my state vector could be set to be x, y, z, for example, or x, y, and the angle. There are different options, but this is one of them. So x, y, and angle. And if I'm moving this way, I'm changing, let's say, the x coordinate, and now I'm moving the rotational coordinate. So in such a case, I'm going to be described by 3 independent variables. We can change one of them without changing the others. And what is control exactly? Control is a signal that we are going to apply to the system. It will live in another space. It will have another dimensionality, m. And in this simplest case, my control could be set to be 2 linear velocities and 1 rotational velocity. So now I'm doing some control that is non-zero in all the directions. I'm applying control the velocities, and these velocities are being integrated so that my state is changing. Our systems are usually described by a system of differential equations in such a form. X dot is equal to some function f of the state vector and the control vector. If something is not clear, please ask me. So this description of the system is understood by the control engineer, by the one who is designing the controller for the system. And we are trying to find the proper control that is going to drive the system to the proper place. So let's consider a specific example. Let's say that you are trying to drive a cart in a supermarket, for example. So your cart is over here, and this is the x-axis. It's described by a single variable x that is not vector, I mean just the coordinate. And you are standing here, the cart is very heavy, and you can apply force to this cart. You wanted to approach some x hat. So what is the intuitive thing to do? The intuitive thing is to apply the force to the proper direction. And if this thing is frictionless, you will apply the force. This cart will start moving, and then you will have to apply the force in the other direction so that the system will stop exactly here. In such a case, our vector x will consist of a single component, which will be x scalar, this coordinate. And the control here will be a force that you're applying. We can write a differential equation that is describing, in order to write the differential equation, we really have to consider the derivative x dot. I will clarify that in a second. So let's say it would be better to say that our system is described by two things. The first is the x coordinate, and the second is the velocity. So it's x dot, the derivative by time. And what is the form of the differential equation that could describe the evolution of the system? We know from basic mechanics that for this block, the following second Newton's law holds. So there is something to work with. Let's try to describe this system with this formalism. So how can we do that? First, we can say that this vector x bar dot consists of two components. We are differentiating this vector, and we're getting the following vector. Here's x dot, and here it's x double dot. I have just differentiated this vector and obtained this vector. Is it okay so far? Please give me a piece of feedback.
Yes, it's fine.
Great. So now we can proceed and we can incorporate this second Newton's law into this equation somehow. So what we can do here, I'm going to do it with other color. I hope it's visible. So here I'm going to write the form of this equation for this system. So it will be x dot, x double dot, and I'm stating that we can assume this function to be linear, both in x and u, the control. So I'm going to formulate this, the dynamics of this system in the following form. I'm going to do it this way. Here is u. So here I'm going to write x and x dot, which is just the state vector. Here is our, oops, it's better to write F, the force here. So F. And this is our control vector. And these are two matrices that we do not control. They are the properties of the system. So let's find out what these matrices really are. And the operations that are going on here are matrix multiplications. So our state vector here lives in the space R2. Our control vector lives in space just R. Clearly, the x bar dot vector is two-dimensional as well. So in order for this formulation to work properly, we have to have these two parts in the right-hand side of the equation to be vectors. So this multiplication of matrix and vector should be a vector, two-dimensional vector, and this as well. So this matrix, we're going to call this matrix A, is going to be from the space of the matrices 2 by 2. And this matrix is going to be, we're going to call this matrix B, and it is going to be from the space R2 times 1. So let's find out what are the values in these matrices. We have to find out 6 values. It's fine?
Yes.
Yep.
Okay. So let us try to begin with the B matrix. So what do we have here? We have a matrix multiplication that in this case boils down to multiplying 1 by 1 matrix, which is basically a scalar, by both this component of the B vector and this component. So this component is showing us how does the force F affect the velocity, the speed, the derivative. It doesn't, because here we have an equation that is saying that F is changing the acceleration, but not the velocity. So it's a differential equation, and it holds at each moment in time. Still, of course, the force will change the velocity, but just over time. Momentarily, the force is changing only the acceleration. So here we can write 1 over m, because here the acceleration is going to be equal to, let's forget for a moment for what is going here, but here it will be F over m. And the velocity, the force is not changing the velocity anyhow. So here we're going to have 0. And now let's check what's going on here. We can do that. We can do that in more detail if it's needed. So is it needed or not? Do we have to go slower or we don't? Please give me the feedback. I really need that to modify the
I think
speed.
this is fine so far.
Okay,
Yeah.
great. So we have 4 elements to figure out. Let's, I'm going to erase this. And I'm going to multiply these matrices just directly. So it will be A11 here. We have to obtain these coefficients in somehow. Here it's A12, A21, A22. And I'm going to multiply them and write down the same thing, but on the left with the matrices multiplied. So what are we going to get? Going to get x dot, x double dot in the vector, and it's equal to basically another vector. So we're going to multiply this matrix by this vector. It's A11 x plus A12 x dot plus 0. 0 is from here. And the second element of the matrix is A21 times x plus A22 times x dot plus F over m. So now we're going to look at this and analyze what could be the values of the coefficients. So first of all, we can see that the thing in the first line on the top here, it is equal to x dot over here. So the coefficient A12 should be 1. And in order for this equality to hold in the first line of the equation, A11 should be 0. And what is going on here? Well, out of this equation, we can say that x double dot is not dependent neither on this element nor on this element. So those are 0, 0. And now we get the final form of this equation. I'm going to write it explicitly. So x dot, x double dot. I have a tendency to randomly use different markers at different moments in time. I hope you can see the red. Yeah, you can. So what this matrix is going to be is just 0, 1, 0, 0. X dot plus 0, 1 over m times the control vector, the force. And this is the exact form for the system of the equation that we were talking about previously, which is x dot equals f of x and u. Vectors, of course, vectors everywhere. And I'm going to skip over those bars from time to time. You can catch me on that. I'm going to correct myself. So this is the system that we have described in terms of the state and control space. After that, we could be interested in driving the system to the desired state. What could that mean? We have to derive some kind of control law that will allow us to change the state of the system. The control law should be a function u of x. So this will be the control vector. This will be the state vector, and this is the function that is mapping the inputs that we see to the outputs that we exert on the system. This is the very, very general form of what we are doing, really. So this applies to a wide variety of systems. We can say that in some generalized form, it holds all the time. What we're basically saying, that we have some state at the current moment in time, and we are reacting to this state by mapping this state to a certain control. This is what's happening. And if we're trying to, say, dynamically stabilize this cart, we can observe the state, and if the state is 0, we're not doing anything. That's fine. And if the block has moved out of the desired state, we're going to counteract so that the cart will reach the desired state again. Are there any questions so far?
Clear.
Clear. Okay. Do you see the connection between this and the multi-dimensional robots? Is there anything that is not matching between those big real systems and these small systems? Okay, so I assume that it's all good. Are you familiar with Lagrangian mechanics?
No.
Mm-hmm. Okay, did you have differential equations or analytical mechanics, theoretical mechanics, something of that kind?
I had the differential equations course.
Great. So let's talk about another system. The system will be very closely related to the humanoid robots, really. We're going to talk about a pendulum. So just once again, please interrupt me if something is not clear. I'm going to say that all the time, and I really mean it. So let's be on the same page with all these things. Now we're going to describe a pendulum. But first, how exactly is it connected to the humanoids? Let's try to simplify this complex system of a humanoid robot that has 20 degrees of freedom. So it has arms, it has a head, the head is moving, and so on. And the robot is trying to see the environment. And we have 2 legs, one in the stance phase and one in the swing phase, or it's kicking the ball. So what can we see here? Here we can see that this foot is in contact with the surface. So if we are going to exert some torque over here, the robot will be acted upon by this torque. So we can incline the robot left or right we can create with the torque in this servo motor, we can create a rotational acceleration for the robot. So let's suppose that something happened, maybe a ball kicked the robot somehow, or a person pushed it. That's not that much important. So let's assume that the center of mass of the robot has moved to the left, and this vertical axis has inclined so that it's now not vertical. My hand drawing is just awful. Okay, I'm an engineer. I can do that. How can we simplify the robot basically? Okay, so we can do the following. We will limit ourselves to considering this robot in a short time span, while it's not changing the foot at which it's standing. It's just standing on one foot and someone has pushed it. Like one-legged balancing, that kind of thing. We can assume this leg to be in constant contact with the surface. So we'll assume it to be tied to the grass, to the surface, to the field. And we're not really interested in describing the entirety, the whole complexity of the state space of this system. We're not really that much interested in the angle of rotation of the head or anything like that. We don't need that. We have to counteract the force that has acted upon the robot. So what we're interested in is the desired position and the position where we are at the moment. And we can simplify this model of the robot to a mass that is, well, I'm simplifying maybe a bit too much. Let me make the model a bit harder and then simplify it properly. So this robot is not really a point mass, not really. But it could be a physical pendulum, so to say. So it's a bar with mass that is distributed somehow, and we can make the mass and the moment of inertia of these two objects equal. So we can just consider such a model of the robot, and in further derivations, it will be simpler for us to consider just a very simple pendulum, like mathematical pendulum. It doesn't change much of what's going on, but the math will be just more clear. So instead of this physical pendulum, I'm going to work with the mathematical pendulum, and the rest of what's going on will be the same, except for the moment of inertia being included. So it's possible to do that. We'll just simplify to the very simplest form that we could achieve. So what is the state space here? It will make sense to assume this system to have a description of the following form. So the vector x is going to consist of the angle theta and the angular velocity theta dot. Why so? Well, for the angle, it's pretty clear. Because we want to drive the robot to the vertical position. And for the angular velocity, well, it's clear again, because if the robot is moving back with some non-zero angular velocity, its angle is going to change over time. So we have to take care of that as well. And we could assume our control to be the torque that we exert in this ankle pitch. So it's like in the airplanes. Pitch, roll, yaw. And this is pitch. So torque and pitch. It's a one-dimensional control. Is it clear so far?
Yes.
Great. So we have another thing to consider. There's a field of gravity that is acting upon this system. So we have to add the length, we have to add some mass. It could resemble numerically the mass of the robot, but yeah, now we're working with this system. And now we are going to, yeah, this is called the inverted pendulum, because the position that this system is supposed to be is the vertical, and it's an unstable equilibrium. But now we're going to downgrade this problem one more time, and let's consider just the simplest pendulum, the normal one, like from the mechanics course. The system description will be actually similar. So let's assume that we are exerting some torque over here. Probably there is a servo motor that is acting on this pendulum, and also gravity, length, mass. So let's find out the equations of motion of this pendulum. What do you think about that? Would you like to do it on your own?
Why did we change it to a standard pendulum if the force of gravity's direction is different?
Yeah, that's for us to consider this system first without control, just how is it going to behave? Clearly, this system will oscillate near the equilibrium state. And this system is different to this one in terms of the equilibrium being unstable. So we're going to talk about that as well. We're going to simulate this pendulum. But first, let's just, for simplicity, start with analyzing this system. So we are going to unroll that back for sure. We are transitioning from the whole and complex system to the simpler one. And now we're going to work towards obtaining some instruments to analyze this thing. And we're going to apply these instruments to the inverted pendulum later. So what we basically want to do is we want to describe the system in the same form. We want to obtain the equation, the differential equation that is going to describe the dynamics of the system. Well, at first, there will be no control. So what I'm saying is that now we're going to write some differential equations that are describing the behavior of the system. Then we're going to try to simplify it. And after some simplification of these rules or of this behavior of the system, it will be much more clear for us how to drive the system to a desired state. For this pendulum, we can try to drive it to the state when it's hanging just below and not moving anywhere. And for this pendulum, we will be interested in reaching another equilibrium state, then stable equilibrium state. But the line of thinking is really similar. So let's try to derive the equations of motion for this thing. Would you like to do it on your own with pen and paper?
Yes. There is yes.
Great. So let's hang on for some time. And after that, we will discuss the results. We'll compare what you have got.
By the way, is this considered a MIMO system or SISO system?
It's a SISO system. So the single output is the control, and single output is the angle.
Okay.
Tell me if you need a break or anything like that. So I'm open to any kind of feedback or comments or whatever. Nasiba, Bushra, and Mohammed, are you going to derive the equations of motion on your own or not really?
Hi, I'm actually busy with something else in parallel, so
Okay.
I'm with you,
Okay.
but not 100%. So
Okay,
maybe
got it.
later.
Got it. Okay. How much time do we need for that, Abdullah? What do you think?
Okay. I found the forces on the mass.
Mhm.
So there is mg downward,
Uh-huh.
and to the bottom left,
Yeah.
is mg cosine theta. I think that's all the forces.
Are you sure about cosine? Let's make the sanity check. Okay, so if theta is 0, the force to the left should be 0 because the pendulum is not moving.
Oh, it's yes, sine theta. Yes.
Mm-hmm. So let's introduce this into the analog of the second Newton law for the rotational motion. I think we can do that. Because we will have to introduce the torque, or it would be better in linear form. I don't even know. I think it's better with, let me think a bit. They are equivalent, but okay, let's do it in linear form. So we basically have this, and the force that will be acting on this mass is equal to tau over L, because this is the torque, this is the length. The bigger the length, the smaller the force. I'm going to divide the whiteboard like this, if you don't mind. Okay, so I'm going to continue over here. And what's about the linear acceleration? The linear acceleration will be the angular acceleration times L, right? And also, excuse me, the sum of the forces, right? So the first force is from the servo motor. The second force is the one that we have found. Mg sine theta. Let us check the signs, by the way. So the positive direction is counterclockwise, as usually in math. So if the angle is like this, the force that is acting by this rotational axis, I mean the one that we're using, our axis is rotational, and this is the positive direction. So I claim that this force will be counteracting the positive theta, so to say. So here we're going to have minus. Do you agree? You can catch me on mistakes if I do them. I don't do them intentionally, but it could happen just occasionally, randomly. So do you agree with everything here?
I'm not sure about the negative sign.
Okay, so let's suppose that the angle is positive, maybe positive 30 degrees. What effect are we going to have is that the force of gravity being projected will try to decrease the theta coordinate, right? So it will try to move the pendulum to the left. It will counteract, it will act in the opposite direction. So when the sinus theta is positive, the force is going to be negative.
Okay. I understood now.
Yeah, okay. So we have these two forces. We have this second Newton's law, and this is basically x double dot. So let's write it down in compact form. It's tau over L plus mg minus mg sine theta, and it is equal to m L theta double dot. Okay. Also, we can rearrange stuff. a bit. Let's multiply by L on both sides. And I'm going to, yeah, it's okay. Yeah, just multiplying by L. So it's going to be tau minus mg L sine theta. And it's equal to m L square theta double dot. What is fascinating here is that we have naturally came to the formulation of the second Newton's law for the rotational case, because this is exactly the moment of inertia of this pendulum. You see?
Yes.
Great. So we could, if we want, substitute that by I. And yeah, let's just observe the structure of this equation. What is it saying? It's, first of all, it's tying together the second derivative of the angle and the zero derivative of the angle, which is just the angle. So here we have our torque, and this is the part that comes from the gravity. So this has the units of torque. This has, again, the units of torque because it's moment of inertia times radians per second square. And this is, again, measured in Newton times meters, because this is the force. This thing is the force. It's multiplied by range. What's the word? Yeah, just the length of this pole. And this is, again, torque. So torque minus torque equals torque. That's the rotational second Newton's law. Let's now imagine that we don't have any torque applied. So the pendulum is just swinging. Let's write that down on the right side of the whiteboard. What do we get here? M L square theta double dot is equal to minus M G L sinus theta. We can get rid of the mass and the length, and here second power goes away. So it's L times theta double dot is equal to minus G sine theta. Or you can write it down as theta double dot is equal to minus G over L sine theta, which could resemble the equation of motion of a simple pendulum, which it exactly is, but we just get to it with all the details. And what is it saying? It is saying that since G is positive, L is positive, and there's a minus sign, the angular acceleration of the pendulum will be of the negative sign of the angle itself, which makes sense. So if the pendulum is, say, to the right, the acceleration is going to be directed to the left. That's what's happening. So we can do some programming today. What do you think about that? Do you have, who of you has installation? I think all of you have installation of Python, Anaconda, Jupyter Notebook, something like that. All of you have that, right?
Yes.
Great. So Mohammed Bushra Nasiba, are you comfortable with do doing some programming.
Right now?
Yeah,
Okay, let me open my laptop. Just give me a second.
yeah, sure. We can do a little
Okay.
break if you want. I think we've been talking about this for an hour already. Gosh, got my hands dirty. When you're using chalk, you'll in chalk just cover from head to toe. And if you're using markers, it's the same story.
I just want to ask,
Yeah.
if I want to control a MIMO system just for a closing for the control part. If I want to control a MIMO system and I want to learn how to model any MIMO system, what course do you recommend I should learn?
What kind of MIMO system?
Like let's just say a robotic arm, like 3DOF.
3DOF.
Yeah.
I can name a few topics that would come handy in such a case. So let's do a little break. You can get a cup of tea or something, and I will do that as well, but later. First, I'm going to outline a couple of things that you need to know to control an arm. I'm going to draw it here. So it could make sense to do some kind of control like this, or more specifically, well, you for sure will have to describe the system. That's for sure. The 3 degree of freedom arm is usually working like this. So it has 1 rotational degree of freedom that is moving the arm around the vertical axis. This is the first actuated degree of freedom. The second is inclining the robot like this. And the third one is the elbow. So what problems are usually solved with such manipulators? Manipulating objects. And what does it mean, really? Well, it means exerting forces to the objects and exerting torques. So exerting wrenches. In order to do that, you will first need to know a bit about sensing. If the robot is doing open loop, you don't need that, but let's just assume for the sake of generality that the robot is reactive. So first you need some kind of sensing. If this robot wants to pick an object or something, it has to be capable of observing the state of the system. So there should be a camera or something of that kind, sensors, lidars, whatever. The first is sensing. The second, or it could be a part of sensing, but I'll just outline that explicitly. It's let's call it perception, okay? Oh, perception. It's not an exactly right distinction, but by sensing I mean just installation of some kind of sensors over here for the object, encoders that will give you the feedback in the joints, all that kind of thing. By perception, I mean that you want not only to see the object, but you would like to know its coordinates. So you will need some kind of the world model. You want to know the coordinates of the object in order to pick it. The following part is the planning. because there could be certain limits to what you can do. You're limited by the speeds, by the velocities of the motors. You're limited by the torque. You cannot lift just any object with a small manipulator. You could be limited by certain obstacles. Let's say that there could be an object that you don't want to disturb, so you'll have to crawl somehow to the object. It would make sense to create some kind of safety net around this robot so that it will not hurt anyone. So there is another constraint. The robot is not supposed to leave this cube and just do random stuff. So it's planning. What you really want to do is to perform the planning for this robot in order to obtain the control, like this one, but it will be three-dimensional. So planning will give you the control. And then the motion or execution or whatever is the naming, I'm going to call this motion. You'll have to give commands to the motors. You will have to think about the speeds, the protocols, all that thing. So you will have to ground the system back to the physical world. The first place where the system is touching the physical world is this. The second place where it happens is this. So in terms of the sensing, it could make sense to check some courses on computer vision, really. In terms of perception, well, basically the same or a separate course on perception. But the course that I'm supposed to give on computer vision, it includes the geometrical model, so it's fine over here. Regarding the planning, it could come handy to check some courses on algorithms, even data structures. Path planning is very important. I mean, graph searches and other branches of discrete mathematics. Are you familiar with graphs?
I took data structures.
Yeah,
course.
okay. So this you can check this. This is this is fine. So this you already have this. It could sound a bit counterintuitive, but you can reduce planning here to a graph search. Really, you can do that. And regarding the motion, well, some course on motion. Well, for example, this one. Well, I'm not sure if we're going to talk about this further, but this course is fine. If you have some preferences, some other courses in the university that teach the same stuff, you can go there. There's no problem. So that's the general outline, I can say. And about these specific topics, well, PID control, yes, it makes sense because PID control is just everywhere. It will be in each of the servos. So it's better to understand the ways in which it works, how to tune them, how to do that. We can tune a PID controller, by the way, just by hand. We can do that in simulation, I mean, not with a physical robot.
Okay.
Yep. So should we have a break?
Yeah, it's okay.
I think so.
Okay, it's okay. You mean yes or no?
We can have a break. Yeah.
Yeah. Okay. Let's have a break. So it's 19:15 Moscow time. Let's be back in 10 minutes. It's okay?
I guess yes.
Yeah,
Yes.
great. So
Yeah.
8:25 UAE time.
Okay, deal.
Okay, so let's continue. How are you feeling? Are you tired or it's fine?
Hello. Yes. Yes, it's okay.
So I can talk in more detail about this or some other general concepts. So there are a few of us, we can talk about anything that is of your interest. Or we can continue with pendulum. So yeah, maybe let's do a bit of programming. Okay. Guys, are you okay with some programming of the pendulum?
Yes.
Great. So let me share the screen. So we're going to do some simulation. First of all, it will be in just graphs and plots and all that stuff. And after that, if we'll have time in this session, we'll do some visualization, just visualization of the pendulum. Otherwise, we can do it next time if it will be okay to carry on the course with the control in mind. So we'll see. I have to be in line with what Professor Hamad wants and so on. So I have to adjust to the needs of the team. You can follow along. I will comment everything I do. This is a library for visualization. And we're going to create our pendulum. So theta, let's say at the initial moment in time, theta will be 1. I mean, floating point. Theta dot. Let's say that it will be 2 radians per second. Too much. 0.3 radians per second. We'll have to keep in mind the units. Now, let's define the parameters. L, 1 meter, G, 10. There's a running joke that G is approximately equal to pi square, which is 9 something. And after that, we're going to run a loop. And we'll have to define the number of iterations that we are going to run the simulation for. So let's say 100 simulations. After this simulation, we are going to plot the history of our simulation. So we're going to plot x over time and v over theta over time and theta dot over time. Please give me feedback if something is not clear. Ask me. Again, there are a few of us, so let's have a lively discussion about that. So it will be data, history, and theta dot history. I'm going to do the proper naming. So first of all, we'll have to propagate the system forward in time. We'll have to define the new, we'll have to calculate the new theta and new theta dot. Yeah, first let's save the previous values. And theta dot. And then we're going to propagate the system. So we're going to check with this equation over here. And we're going to act according to that. So theta, refreshed theta will be equal to something. We're going to write that. And theta dot will be something else. And we're going to plot both of these lists. So the only question is how to define these two things. How are we going to find the values of theta and theta dot at the next instant in time? We'll have to define what is exactly new instant in time. So we're going to define some dt, which is the smallest incremental step in time that we're going to consider in our simulation. Clearly, our simulation is discrete, so we are going to have not the continuous flow of time, but the discrete timestamps, first, second, third, and so on. And each new value of this iterator will correspond to a certain new discrete moment in time. Erase these schematics. And we're going to talk about some simple mechanics here. So we know that the velocity is 0 plus an integral from t0 to t1 of acceleration from time dt. However, if the time between t0 and t1 is sufficiently small, we can approximate this to be close to v0 plus a delta t, where delta t is t1 minus t0. Or it will hold in case of the constant acceleration. So for us, it will be not valid really, I mean, for a prolonged period of time. But in, say, undisturbed linear motion, it holds. Oh, no, in undisturbed linear motion, it's the acceleration is 0. I mean, for non-changing acceleration, it's true. So what we're going to do is we're going to extrapolate that to rotary motion, and we're going to say that theta k plus 1, the next theta dot k plus 1 will be equal to theta dot k on the step k plus theta double dot times dt. Is it okay so far?
I didn't understand why we put theta dt.
So you don't agree with this part or this part?
Yeah, the top part.
The top part, this one. This slide,
Yes.
right?
Yes.
Okay, so what it says is that at the first, let's say that at the first moment in time, we have some velocity v0. This claims that at the moment t1, the velocity, this one, v1, will be equal to the initial velocity plus the integral of the acceleration during that time period from t0 to t1. Do you agree with this?
Yes, it makes sense, yes.
Yeah. And now we are going to perform a trick with approximating. So here it's not equal, it's almost equal. It's it's an approximation, basically. This is what we're doing. We can also, if we are into analysis, we can say that it's plus, it's exactly equal to this thing plus small o of dt. You know the Taylor expansion, that thing. So we're going to extrapolate this part onto the rotary motion, because this is the full analog of the velocity is the rotational velocity. And this is the rotational acceleration. Now it's okay?
Yes, I get it now, yes.
Yeah, great. And we are introducing the sub-indexes k plus 1, meaning the next timestamp, and this is the previous, oh, excuse me, here should be theta double dot sub k. So where I'm going with this, now we're going to tie this together with this equation, because here we can place sub k and here sub k again. What this says is that we have got the closed form for the velocity in the next moment in time in terms of the velocity in previous moment in time and the acceleration, which we have over here. So I'm going to write this just for the completeness. So it's theta double dot k, and it's equal to minus g over L sinus theta k. And we can plug this over here, which will give us theta dot sub k minus g over L sinus theta k. This is what we need to perform the propagation of the system further in time, because here we're using known values. We know the previous velocity and previous coordinate, and we can use them to calculate the next velocity. That is what we're going to do. And the thing that we have to do next is rather simple, because we are going to say just the same argument, but for the angle. So I'm saying that theta k plus 1 without any dots will be equal to theta k plus the angular velocity k times dt. So now we're going to use, I'm going to encircle this. So this is the first thing that we need. And this is the second thing that we need. The marker is not working. Where is the working marker? Okay, I think I have, here. Yeah, so we're going to use, sorry for the mess, we're going to use this equation and this equation. And using them, we're going to propagate the system in time, because here we have got the expressions for the next coordinate and next velocity in terms of the previous coordinate and previous velocity. The same here. Yeah, previous velocity and previous coordinate. Does it make sense?
Yes.
Great. So now we can do the programming. We have defined basically everything we need. So let's do exactly that. I'm going to write down this line with the code. Theta is equal to theta plus theta dot times dt. Or yeah, it's better to say theta nu. Theta nu. And theta dot nu, meaning the next one. So we did the second line in code, and now we're going to do the first line in code. It will be theta dot old minus g over L times math dot sine of theta old theta times dt. Is it okay?
Yes.
Yeah, I think it's correct. Oh, excuse me. I forgot the dt here. Sorry. Delta t, I mean delta t. Yeah. Now it's correct. I did it properly in code, but forgot on the whiteboard. Yeah. So now we can run it and observe what trajectories will the system go through in terms of the coordinate and velocity. Import math. Yes, we need that as well. Sorry. I have we have obtained the new coordinates, but we have not rewrote the old ones. That's why the coordinate is exactly 1 all the way through and the velocity is 0.3, but I'll correct that. So theta is just equal to theta nu and theta dot is equal to theta dot new. Now it should work. Yep. So what do we see here? The pendulum was, or we can do this plot separately, basically. Well, then let's show. It will be more clear. Yep. So this is on the top, the evolution of the system coordinate. It started from 1, then it swung through 0 to almost -1. We can increase the number of iterations, and it will be a very familiar sinusoid. You can ask, why is it diverging? Well, but that's the problem with numerical integration. I can fix that for now, and then we will discuss it in more detail. Because for now it's not necessary. I'm going to just fix it. Okay, so just like this. Yeah, now it should not diverge. Yeah, so what we have here is the trajectory of the coordinate. To the right we have time, and this is the trajectory of the velocity. By trajectory I mean what exact values did it have at certain moments in time. And this is the normal sinusoidal motion. Is it clear? Guys, is it clear or not really? So do we have to reiterate through something? Guys, your microphones are off. Do you hear me?
Yep, I can hear you.
So is it clear with the code, or we have to clarify something?
For me, it's okay.
Okay, so now we can try to visualize this pendulum. What do you think about it? We can draw it.
Can you please print the canvas variable?
Canvas variable, yeah, print.
Yeah.
You mean?
I just want to see how the like what's
Ah,
inside.
yeah, sure. Just a sec. We have to specify that it should be uint8. Excuse me, I forgot that. That's why the whole screen is blank. I will print it in a minute. So let's just make it work. Yes.
Take your time.
Yes. It's working. So there's a pendulum swinging, and I'm going to do it in just a separate cell. So let's check what's that exactly. So let's print first the canvas itself, then let's print its shapes, canvas.shape, and then let's print some element of canvas. Let's say element number 100, 300, 2. So what do we get here? The first annoying long thing is a list of all the elements. I will comment that out, okay? So yeah, now it's better. The shapes of this array, of this three-dimensional array, is 700 by 700 by 3. By 3 here, we mean red, green, and blue components of the color. We output the arrays on the screen. Normally, as you would expect, with red, green, and blue color, they are, I mean, that's a default. It's usually done by the in that form, and all our monitors usually support 3 colors, so we use the same thing. And by creating the array of ones and multiplying it by 70, I get this. Oh, let me. I'm getting this. 70. I deleted. Yes, here. So 70 is this shade of gray. That's what's happening with the canvas. And as a separate element in this canvas, we have, of course, 70, because this is exactly the value by which we have filled the whole array. So I feel like accelerating that by a bit. We can make the DT coarser, and also it would be nice to initialize the pendulum with a smaller value, 0.4 or something. And it should nicely swing. Yeah, it does. So you can see that its motions are clearly discrete, and it's moving in jerky motions, but still, its behavior makes sense. It really does resemble the real pendulum. That's what exactly we wanted. Guess something is going on. Wi-Fi disconnect. Yeah, I think you're back. So no problem. Yep. So this is the simple visualization of the pendulum. I can share this whole code. It's very brief. Can send it in the chat. Even just like this. So you will have to install OpenCV library, this one, in order to run this thing. Yeah, it's the simulation has completed, by the way, so it has performed that much oscillations. And you can install the library by this command. So is it fine so far?
All good so far.
Okay. Abdullah.
Yes.
Okay, great. So let's proceed. Let's try to control this pendulum somehow. So what I propose to do, our simple control law will be, if the pendulum is moving to the right, we will slightly push it to the left. That's what I propose to do. So we will try to stop it from moving. And it could be done here, because here once we said that we will assume theta to be always 0, and now we can say that no, now it will be not 0. So from this equation, theta double dot will be equal to the same thing that we already have, plus theta over ml square. And yeah, so both of these things will be multiplied by dt. Yeah. Theta over ml square. Like this. So, oh, theta, I mean tau, torque, control, tau, not theta. So now we'll have defined tau somehow. But if we say that the pendulum moving to the right will result in us pushing it to the left, we can say that tau is just minus theta dot. So we'll be counteracting the pendulum. We'll be trying to slow it down. And let's add some small coefficient over here. Let's check what will happen. Really? Yeah, there's no mass indeed. 1 kilogram. So do we observe any changes in the amplitude? I think we do. The pendulum is really slowing down. So this was our first simplest controller that is driving this dynamical system to the 0 state. Let's make sense of it. So is it all good?
Yes.
Awesome. Let's check the plots. Yeah, so the plots are, as we could expect, they are both approaching 0, both 0 velocity and 0 position. Great. Can we do it better? Can we increase the coefficient? Maybe just 1. Let's try. So it slows down considerably quicker. And this could start resembling you something. There were questions about PID. This is very close, because this type of control is basically suppressing the velocity. We are doing the decontrol. we are counteracting the speed of the value that we are trying to control. So out of the whole PID, we are dealing with D here. And how would a P controller look like? It will be just -1 times theta, or minus, say 0.5, I don't know. So if the pendulum is swinging somewhere in the right side, we're going to push it to the left. What will happen in such a case? Seems a bit odd. We are trying to move this pendulum towards 0, but somehow the amplitude of the oscillations is not decreasing. How come? The point here is that we have added just another term that acts exactly like, well, not exactly, but closely to this term that we already had from the gravity. The gravity is doing kind of this similar work. The gravity is trying to move the pendulum to the equilibrium. But since there is no dissipation in the system, the pendulum overshoots each time. We can even make G equal to 0, and we'll check how would it look like without any gravity. So it's like a space pendulum. Since we are explicitly acting in the direction that is opposite to the offset of the pendulum, we are doing almost the same thing. The difference is that we are acting proportionally to the deviation from 0, and the force of the gravity is acting proportionally to the sign of that deviation. But in the close proximity of the equilibrium state, they resemble each other pretty closely. So we can get back the mighty gravity, and let's try to combine both, counteracting in terms of theta and counteracting in terms of theta dot. Yep, it's working. So let us try to drive this pendulum to a non-equilibrium state. Can we? Guys, please tell me, can we continue? So are you tired? Are you exhausted? Is it all good? Is it too obvious, or is it complicated, or is it fine? Give me a piece of feedback.
It's a little confusing, but I am following.
Great, great. That's important. Okay, so what we're going to do now is we're going to try to stabilize this pendulum, not in the vertical position, but with some offset. So here, what will happen is that the force of gravity will constantly try to move this pendulum towards vertical position, and we'll have to deal with that somehow. So first of all, let's try to define some desired theta. Theta desired, and let it be 0.5 radians. So here we're going to counteract in terms of the position, not the deviation from 0, but the deviation from theta desired. And also let me draw the desired position. Yeah, desired position. So that we'll see where are we going actually. Okay, and let's change the color. Let it be muted, kinda, and thicker. So it will be our goal position. We'll just see where are we going. So the not moving thing on the right is the desired position. And what do we see here is that the pendulum has already stabilized, but it's kind of inclined to the right. So we're doing something correctly. Let's work with that. Let's, I know. We can plot, on the same plot, we can plot the desired position. Yes, that's what we will do. Plot. And here we will have a list of theta desired. It will be just filled with theta desired. No iterations. Like this. So, yep. Let's check. So the yellow line here is the theta desired. Let's try to increase the proportional coefficient. Here it's this thing is the proportional coefficient. So I'll write the whole name here, PID, and K proportional will be, now it's 0.5. So I'll stick to that, and we are going to change it soon. KP, and here it's KD, the differential coefficient.
Does it mean that it didn't reach the desired theta?
Exactly. We can observe it by checking the simulation. The desired position is the blue one, and the pendulum, you have to look closely. So it's a bit inclined towards the goal position, but it's not there by any means. You see, now it's stable,
Right?
but it's not vertical. It's in the, so to say, lying in the right direction, not going in the right direction, but lying in the right direction. But we can work with that. We have a signal and it's converged somewhere. Let's
how
increase.
There is negative values, but it's not going to the left side of the in the simulation. Does the minus sign means that it goes in the other direction?
You mean this minus sign? Or
in the graph? No,
in the graph? Okay, so
yeah.
zero here is the vertical position. And to the right, it's positive direction. To the left, it's negative direction of the angle.
Okay.
So both of you follow along with the concept of this PD controller, right? So now we're going to tune it. So far, it's good?
Yeah.
Okay. Now let's increase
Yeah.
Awesome. So let's increase the P coefficient. Let's make it not 0.5, but just 5. You see? It's closer. Let me set the limits. I think it would be better with the limits for us to have the same scale, because it's PLT is setting the limits just based on the data. Okay, how can I quickly do that? PLT plot limits. I always forget how to do that. Access range, stack abuse. Awesome naming, I should say. Really. So I have to do this thing with PLT, what's the name of this thing? Okay. No. X, I need Wiley. Hold on. So it's yeah. Wiley, indeed. That's kind of intuitive. Okay, so I have to do it here, I believe. But Wiley and from say -2 radians to 2 radians. Hope it helps. Yeah, that's working. Great. And let's start from some position that is worse. Let's start at, I don't know, -1.4, and we need to get to 0.5. So let's check it out. It's swinging, and at some point it's going to approach what we need. Or not exactly, but kinda. Okay. Let's close this tab. I think it's somehow using too much
Is
memory.
it even moving?
Yes, it is. I think there were some lags, so let me rerun it again. Okay. You see the simulation?
Oh yeah.
Yeah. So it started very far away, then it started swinging with less and less amplitude, and now it's stuck somewhere. And the most interesting thing is the plot, because it's becoming better finally. Let us even set the desired position to be 1.5 just to be even more far away, and we can increase the differential coefficient for the pendulum to swing to dissipate the energy faster. And here let's, I don't know, set even 25. So let's check what will happen. You see? So the coefficient of 5 in the differential part is so harsh on the velocities, so that the velocity is becoming very small quite fast. You see?
Yes.
Yeah. So now we're tuning the PD controller. It's not PID yet, but it's PD. So let's continue. Do you have some intuition on what to do next?
We'll set the integral coefficient, I think.
Yes, really. So we can do that. At first, let's maybe slightly decrease the differential, or not slightly. Let's do it. Let's set it to be 2. I don't know. I'm trying just by intuition. And here, KD, let's let it be 75. So it's very harsh in terms of the required torque. But yeah, the pendulum is static with some constant offset. That's what we really need. So that's fine for us. There were some oscillations, and they were quite fastly damped by the differential coefficient. If we want less of those oscillations, we can set the KD to be greater. Yep. So now there is even no overshoot. No overshoot. We're just following here. If I would not stop the simulation, we will be following the same line. It will be horizontal, so the pendulum will not move anywhere. Now let's create some integral. We'll do it numerically for sure. So integral 0, and here we will just add at each moment in time. We'll add the error, this one, to the integral part. Oh, yeah, that is better to, yeah, it's better to do it separately. So error here is this thing. It's the deviation from the desired position. And the integral will be equal the previous integral plus error. I assume that Ki should be rather small. Let's begin with 0.1 because there are a lot of steps of simulation. So let's check what will happen. And minus Ki times integral. Let's check what will happen. It's moving, but slowly. Okay. I was too conservative with this. You see, it's working. So the pendulum is indeed approaching the desired position, although there's a constant force pushing it down. And seems like it has approached the desired position at this point in time. Yeah, so you can see that pretty clearly. We can increase the integral coefficient even more, and we can perform less iterations for the simulation to stop earlier. Yeah, so it's pretty much here. Enough. Let's see what other plots. Yep. So here we have an overshoot, and this overshoot has counted into the integral error, of course. And after that, we have indeed reached what we wanted. We have stabilized the system in a desired position, despite an external force obstructing our ways. So questions, comments, outcomes.
Isn't this rapid speed can affect the robot afterwards? Like the robot will fall afterwards, right?
Yes,
After
that's
braking.
true. That's true. That's true. We cannot really apply giant torques. You're right. That's a good question. So let's introduce torque history.
So I guess there is a limitation of the speed, max speed, right?
Yes, there is a limitation for max speed and limitation for max torque. You're right. So let's check what will be the torque in ideal conditions when where we can do just anything. So it's a simulation. It will not break anything. So torque history. And here I'm going to plot it. Let's just check the range of the values. Okay, enough. So 200 Newton meters. That's a lot. That's like 20 kilograms on 1 meter. That's a lot of torque. We can limit the torque. And after that, the stabilization time will, of course, increase, but that's fine. We'll just have to keep that in mind. So, all right. Tau will be equal to NP clip of tau minus max torque plus max torque. And max torque will be 50 Newton meters. Oh, no, not 50. Let's say 10. So 10 Newton meters. Is it okay with the pendulum like this? Let's set the mass to be 0.5. Okay, I'm doing that because the maximum torque that the dynamic cell MX106 can give is 10 Newton meters. These are the motors that we are using in the robots. So yeah, and max torque will be 10 Newton meters. So let's check. Let's check what will happen. Seems like we have got some oscillations. There's too much of the integral coefficient. It's kind of overshooting all the time. So let's try again. Or, well, or not the integral, I'm not sure. So some of the coefficients are too big, that's for sure. Maybe the proportional, let's decrease that. Let it be more adequate. Okay, so it's better. The torque is, yeah, it's limited clearly because we have clipped it manually. There is something that we can do better. Maybe the integral coefficient should be smaller. So I'm hand tuning these parameters. I don't know the right values because I picked all the masses and everything just randomly. But that's the controller design. Another issue that we could encounter is too small DT. So we can do it like that. We can disable the visualization. Let's skip that. Will not open the windows. Will not draw anything. But the plots, we'll have the plots in an instant. Oh, really? How come? Okay, so let's check the what. Wait, what? That's strange. Okay. So Haven't I commented anything meaningful? Seems like not. But okay, yeah, let's figure it out. So let's try bigger integral coefficient. Ah, yes, sure, of course. Stupid me. I made the dt smaller. That's why. First of all, let's increase the range. So I'd made the dt smaller without changing the number of the steps of the simulation. I decreased dt tenfold, so now we'll increase the number of iterations tenfold. And the integral part should be much smaller, because we're just summing through all the steps of the simulation, and there were too many of them. Yeah, now it's fine. So what did I do? I decreased the step of the simulation so that this, in order to avoid those jerky movements. I think that those jerky movements were caused by the coarse simulation step in the vicinity of the point that we are trying to approach. So if we are commanding a force, a torque, and then acting with such a torque for a prolonged period of time, for longer than we need to approach the desired position, we'll get some kind of this shaking because we are overshooting all the time, because of the timestamp, not because of the coefficients. And another thing that I did is I considerably decreased the integral coefficient in order for it not to cause large oscillations, because these oscillations, they happen like in the following way. So we're starting off the desired position, we acquire some integral, some sum in the integral, it causes a slight overshoot, and this overshoot causes a new overshoot, and so on. So it could converge for a really long time. We can try that out. Yeah, so I made the integral coefficient bigger, and it caused some overshooting. So that's the basic PID control. And the cool thing here is that you can really apply it to a real pendulum. Well, given a pendulum, of course. If you have a pendulum that is controlled by torque, you can really do the same stuff, exactly the same stuff. Try not to burn the motor, of course, but you can do basically this. And that will stabilize the pendulum with the proper values of everything, of course.
That's amazing.
Yeah, I think so. It's really amazing. I mean, the control as a discipline, it's cool. We can do stuff with robots, but the world is so complex, and we can make the systems go to certain states, to kick the ball or to drive along a lane or something else. So there are cool things that you can do with control. And in this course related to the control, we're going to try different things related to simulating systems. We're going to derive different controllers. They will be much more complicated than PID. Well, some of them are much more complicated than PID. For instance, a linear quadratic regulator, which will require some vector algebra, basically. There's nothing you cannot understand for sure, but it will just require some tedious calculations. think I can show you something. I have some.
Are we going to use Weebots again?
Hmm?
Are we going to use Weebots again? The simulation?
In this course, no, we don't. You will have practice with Fyodor. So
Are we going to
think-
apply it somehow or just in
the control? No, not really. So it's the control that we are talking about here is quite far away from the multi-level control of the real robot. So we will try to incorporate, not exactly me, but Fyodor will first introduce you to the ways to work with the robot practically, and I will be approaching from the other side. I will be giving the basics of control, and at some point it will start converging. Well, that's a long process, really. At first, you will have to form a team, you'll have to start competing, and all the knowledge will be acquired during the process. So we will not be able to implement our own walking pattern. That's very complicated, and that's beyond the scope of a course. We're going to
yeah, fair enough.
yeah, we're going to do sophisticated things, but not for the 20-dimensional robot, really. On the other hand, you will work with real 20-dimensional robot in lab with Fyodor. So let me show you a cool thing. That's from today's seminar on control. Let me run this. Computer is just dying. It's overworked. It's overloaded. Yep. So here we have a dynamical system. And now I'm setting its goal position. So what this system is, it's a cart, this block over here, it's a cart, and the thing on top is a pendulum. So it's called cart pendulum. It's called cart pole. It's a pole, it's a pendulum that's unactuated. You get the idea?
Yeah, I guess.
Yes.
Yeah. So there is like this. There's a cart, and the pendulum is not activated, so it can swing freely. And the point is to apply the force to the cart so that the pendulum stays upright. At the same time, we can make this system approach desired position in terms of the x coordinate. So that's what could be done with the linear quadratic regulator that I have mentioned. And if we're going to talk about control, not vision, we're going to talk about that. But I have to discuss that with Bushra and Dr. Hamad, and we will have to discuss that anyways. So I'm not able to tell just anything that I want. What do you think
Okay.
about this versus vision? So what do you prefer?
Vision, of course.
Yeah,
Vision.
if we start with vision, it will be very nice.
Okay, but Muhammad, you have already had vision.
Yeah.
So you want to go it all over again?
To be honest, I have no problem. 'Cause, it depends on the other students, to be honest.
Yeah. Okay, so choosing between control and vision, both of you choose vision, right?
Yes.
Okay. Okay. So fair enough. I'll consult with the other people involved, and I think we are going to proceed with vision. I think that's it for today.
Yeah. It's already 9:41.
Yeah, right. At my country, it's 8:41, but it's still a lot. So, feedback, questions, comments, anything? Or you're tight and yeah, I got it. Got it.
Next time, can we like make the duration of the seminar a bit shorter? Like
Yeah. Yes. Yes.
maybe
Okay. Like 2 hours
hour.
or 1.5.
Something like that, yeah.
Okay. Okay.
Because we already have a like we came from the university and then we have the seminar. It's
Yeah.
already like the end of the day.
Yeah. I know.
Yeah.
I know that stuff. There's a problem of this course not being in the official curriculum. Otherwise, it would be
Right.
more suitable. But I cannot do it
Yeah,
just
yeah.
by will. I'm not even formally employed in KU, so I'm not a professor or anything. But yeah,
You already do your best, so
I hope so.
we appreciate.
Thank you guys for coming and participating.
Yeah, for sure.
See you next time then.
This is the least thing we can do. Yeah,
Have
see you
a
next time.
nice evening. Yeah. Bye.
You too. You too. You too.
Thanks.
Yeah, bye bye.
Thank you.
See you next Wednesday.
Yeah. Bye.
I have a question. When are we going to do something with Fedor? Like when will we be going to the lab?
I think it's better to ask Bushra about that. I have asked her already, and she was discussing some stuff with Dr. Hamad. So I'm not
Oh.
really up to the current state of affairs, but you can ask her or you can ask Professor Hamad or
Okay, sure.
Fedor.
Okay.
You can write in the chat.
Himself?
Just
I said Fedor himself. Okay, no problem.
yeah, why not? You can write in the chat. All of them are there. So
Okay, sure. Thank you.
yep. Thanks. Bye.
Bye.